Howdy. I'd like to talk a little bit about how to make functions differentiable. And in particular, I want to talk about how to make piecewise functions differentiable. We know already that f prime of c exists if and only if, I'm going to use the double arrow here to mean if and only if, f prime from the left at c is equal to f prime from the right at c. We also learned in class today that differentiability implies continuity. So if f prime of c exists, that means that f of x is continuous at x equals c. Now you probably remember from geometry that the contrapositive of this statement is that if f of x is not continuous at x equals c, then it is impossible for f prime at c to exist, because if it did, then f would be continuous, and it's not. This is, you may recall, the contrapositive of our conditional statement. And if the conditional is true, which in this case it is, then the contrapositive is automatically true as well. So what this does for us is it allows us to actually put two different conditions on our function so that it may have a derivative. Let me show you what I mean. Let's take this question. Find a and b so that f prime of 1 exists. Or another way to put it is so that f of x is differentiable at x equals 1. And our function is going to be f of x equals ax squared plus b for x is less than or equal to 1, and bx plus 2 when x is greater than 1. So this is our situation, and you can see that the top function is some kind of a parabola that is going to have an intercept at b, and it's going to have some kind of steepness that is controlled by a. And meanwhile, my line, my second piece down here is going to be a line with a slope of b and an intercept of 2. And so it's going to have to somehow connect with this parabola so that right here at x equals 1, we have a nice smooth curve without any sharp corner. That's really what we have to accomplish. And so to do that, we are going to use our conditions that the left and right hand derivatives must be equal and that the function has to be continuous. And we're going to do it in this order. First, we're going to check continuity. And in order for f to be continuous, we require that the limit as x goes to 1 of f of x has to equal f of 1. What is f of 1? Well, we go to the point where x equals 1, and we take a look at that piece right here. So that f of 1 is equal to a times 1 squared plus b, or a plus b. All right. Well, what is the limit as x goes to 1 of f of x? I actually have two different limits. I have the limit from the left, and I have the limit from the right. The limit from the left is kind of boring, and I usually skip the piece that goes with the equality because the limit from the left will always match the value of the function. But the limit from the right might not. And so when I check the limit from the right, here, wow, try that again. And I'm going to use this piece right here, and that gives me b times 1 plus 2. And now here's what I require. I require that all three of these have to be equal to each other. The top one is the function value, and the bottom two are the two limits. And so when I set them equal to each other, lo and behold, something wonderful happens. A plus b has to equal b plus 2. And voila, I get a is equal to 2. As soon as I get a is equal to 2, that tells me something about my parabola right here. And I'm going to go back and replace so that I see that the top piece has to actually be 2x squared plus b in order for my function to be continuous. So that was the first condition. Now for the second condition, I require differentiability. I need for f prime minus f1 to equal f prime plus f1. The derivative from the left has to equal the derivative from the right. And so I'm going to set up each one of those. First of all, I'm going to compute f prime from the left. And that's going to be the limit as x goes to 1 from the left of f of x minus f of 1 all over x minus 1. Now, when I compute that, I have an advantage because I already figured out f of 1 back up here when I computed, when I checked the continuity condition. And so I can substitute that directly, and f of 1 was equal to a plus b, which I now know is equal to 2 plus b, because I know the value of a. And f of x, for x's that are less than 1, go back to our piece right here, for x's that are less than 1, f of x is going to be equal to 2x squared plus b. Notice that I made free use of the fact that I already know the value of a. And now when I simplify, something really nice happens, and that is that my b's cancel out, and I get 2x squared minus 2 over x minus 1. A quick check of the form reveals 0 over 0. There is a common factor, and it doesn't take too much effort to find it. It is x minus 1. So that when the dust settles, I get 2 times 2, which is equal to 4. That's my derivative from the left. Now what about the derivative from the right? Do that in a different color. That's going to be the limit as x goes to 1 from the right of f of x minus f of 1 over x minus 1. And again, the f of 1 is already known. It is 2 plus b. But for the f of x, I will use the piece that applies when x is greater than 1, which is bx plus 2. All of that divided by x minus 1, and all of that as x goes to 1 from the right. Well, once again, I have some happy circumstance because the 2's cancel here, and I get bx minus b over x minus 1. And I think we can all see that there is a common factor of b. So that when I factor that out, I get cancellation, and my derivative from the right is equal to b. What does this mean? Well, in order for my function to be differentiable, then the derivative from the left has to equal the derivative from the right. And I found a value for the derivative from the left, and I found a value for the derivative from the right, and so I have b is equal to 4. So this now answers my question, and I package up my answer, and put a box around it, and smile. Let's take a look at a slightly more involved question. Find a and b such that f of x is differentiable at x equals 9. And here we're going to define f of x is equal to a times the square root of x plus b for x greater, less than or equal to 9, and x plus 3 for x greater than 9. Again, we're going to begin with our continuity condition. We're going to require that the limit as x goes to 9 of f be equal to f of 9. And you can see by substituting in x equals 9 into the appropriate piece that f of 9 is equal to 3a plus b. And you can also see that as x goes to 9 from the right, then what I get is equal to 9 plus 3, which is equal to 12. I ignore the limit from the left, not because I don't absolutely need it, but because it's going to give me the same value as 3a plus b. And so I set these equal, and I get my first equation, 3a plus b is equal to 12. This is the result of the continuity condition. Now I do differentiability, and that means that I need f prime from the left at 9 to be equal to f prime from the right at 9. So I'm going to go through and patiently compute each value there. F prime from the left at 9 will be the limit as x goes to 9 of f of x minus f of 9 over x minus 9. And as I go to 9 from the left, what I get is a root x plus b for f of x minus 3a plus b for f of 9. And I see that the b's cancel out right here. And I also see that I have a common factor of a left in these terms. So I factor out the a. And I'm left with this limit right here, which I recognize is a limit that can be done by rationalization. And so multiplying top and bottom by root x plus 3, I've done enough of these to see where this goes, and you can figure out for yourself that this limit leaves me with a times 1/6, or a over 6, as the value of the derivative from the left at 9. Now we consider the derivative from the right at 9, which is the limit as x goes to 9 from the right of, again, f of x minus f of 9 over x minus 9. These problems really do require some patience, just because you end up doing a lot of analysis right at these points. And so I actually only assigned 3 of these problems in your exercises. Notice that from the right, the piece that applies is x plus 3. Minus, now f of 9 is equal to 3a plus b. And all of that over x minus 9. Now at first I look at this limit and I think it's going to be really pretty awful, because it has x's and it has a's and it has b's and so on and so forth. And so I start looking around for something that might possibly help me. But then I discover something from the continuity condition. And that is that 3a plus b has got to equal 12. Which means that I can replace 3a plus b with what it is. And when I do, I get on the top x plus 3 minus 12, which is x minus 9. And of course on the bottom I still have x minus 9, and so I get 1. And so as a result, because f prime minus at 9, which is equal to a over 6, has to equal 1, which is f prime plus 9. Therefore, a is equal to 6. And since 3a plus b is equal to 12 from our continuity condition, then I have 18 plus b equals 12, and b is equal to minus 6. So notice that it's entirely possible that we might end up with two equations and two variables